In this video, we're going to be talking about the mathematical models, equations, and the algorithms of the gray wolf optimizer. So remember, in the last video, we talked about inspiration. So let's quickly recap. The inspirations are two aspects of their social life: social hierarchy and social hunting mechanisms. Now we know the inspiration. For the hierarchy, we know that there are four different types of wolves: alpha, beta, delta, and omega. And the hunting mechanism is interesting. They chase the prey, they harass the prey until it's tired, and then they attack. So try to circle around it again and again. So these are the steps that they take to hunt the prey. So let's start with the social hierarchy. So I'll show you how we can mathematically model that and mimic that in computer and to develop an optimization algorithm. In order to mathematically model the social hierarchy of wolves when designing the gray wolf optimizer, I consider four things. Because if you think about a search space, remember that landscape, the color with one peak and one valley, you can think about multiple solutions somewhere on the landscape, right? Think about a pack of wolves who try to chase a prey. Normally in real world environment, they know where the prey is, they have sensors like eyes and sense of smell, so they can get benefit from those. But if you want to simulate that in a computer, it's very difficult. We can't do that. But what we can assume is that the best solution in a search space that we found so far is alpha, because it's the best solution, and that's the best thing that we can use that solution to find a better one. It's probably very close to the best solution. At least it's more promising, I should say. So the first solution, whenever in the gray wolf optimizer, whenever you're searching, the best solution that you found so far is considered to be the alpha. The second best solution, beta. The third best solution is delta, and everything else is omega. And we have to make the assumption again, as I said, because we don't know where the best solution is in real world problems, right? Or in the example, in the biological example, the gray wolves can see and sense their prey where it is, so they try to, it's a kind of search it and find it and then kill it. But for us, we are dealing with problems with unknown search space and of course unknown best optimal solution. So we have to make these assumptions. At least that's how I design the first version of gray wolf optimizer. There has been a lot of improvement. People consider multiple alpha, multiple beta, which is interesting. It's also one way to improve an algorithm for a particular set of problems. It is safe to say that in the GW algorithm, the hunting is guided by alpha, beta, and delta. Or the optimization process, which is similar to hunting in this case, is guided by those three best solutions. So we always find the three best solution and we'll try to search around that area. If we find a better solution, we update either alpha, beta, or delta. All right, so we have to update them. So in each step of hunt, in this case, or optimization, we have always those three best solutions and we update it every single time if we find a better solution. So that was all about the hierarchy, how to model that hierarchy, or how to make some assumption at least when developing the gray wolf optimizer. That's what I assume at least. In order to mathematically model the encircling behavior, right, how to encircle around the prey, I use the following equation. Again, I'm not going to get into details now because I have a dedicated video to show you the impact of each of the components, and I've got the next slide to show you a simpler version of that. But I'll just go through these ones for now, and then you will understand the impact of each component later. So I've got a vector called distance, which is equal to an absolute value of three vectors: c dot xp, or the position of the prey in the iteration t or time t, minus xt, which is the position of a wolf that we want to update its position, right? This is a pairwise multiplication. I should have used a better notation. It should be here, or it's not dot product, it's a pairwise multiplication. So that means first parameter by first parameter, second parameter by second parameter, and so on. And you might be asking why I use a vector, and that's because I don't know the number of variables that you have in your problem. So you might have two variables, you might have 10 variables, you might have 10,000 variables. In our example, that shape, the optimization problem that we looked in the first video, How many parameters we had? We had exactly 11 parameters. So that vector represents all those parameters, right? So if you find it a bit confusing for now, think about it as one dimension only. That will be then D, no vector, equals to C dot X minus X. So it's kind of the discrepancy between where the prey is, where the current wolf is, right? And then update it based on some constant. So you multiply C by the prey by something, or C, which is a constant, and then subtract it from X. And that's kind of this, it gives you a distance. But to update the actual position, which means if this is the prey and this is my gray wolf, then to find the next position, whether here, or anywhere else around it, in one dimension, it's either this side or that side, can't be in any other place. This is the equation that I used. I said xt plus 1, which means the position in the next step or next iteration is equal to the current position of the prey minus A dot D. Again, this is just a multiplication, pairwise multiplication, and if it's one dimensional, your problem is one dimensional, then you don't need vector. You just say xt1 equals to x prey minus A times D. And I've gone through all these parameters. You don't have to worry about them. So A and C are coefficient. They are changed automatically based on some parameters, and that's what we're going to discuss later on. The vectors A and C are calculated using these equations. 2 times A minus R1 minus A. This is for the for updating the first one, and C is equal to 2 times R2. R1 and R2 are random variables, and they are randomly initialized for every single wolf in every single iteration. Okay, so, and that's why the gray wolf optimizer is stochastic, because of these two random components. Remember, A is linearly decreased from 2 to 0, and there is a reason behind it. You will find out later on, but basically that will reduce the randomness and the movement, the steps of movement, the magnitude of movement proportional to the iteration number. So that means as we get closer and closer to the final steps of the optimization, the last steps, these things get slower and slower because you want to converge it to some point. That's why we have that linear mechanism. Again, these make a lot more sense when I show you the experiment. I've got a few videos to dive into the impact of each of these parameters. But again, you might be asking how I came up with these equations, and that's what a lot of people ask me, to be honest. There is no rule of thumb here. There are multiple ways to do this. You just need to keep trying, and of course you need to talk to experts in that area, those who investigate how these guys maneuver, how these creatures hunt, and the idea came from a discussion with a few friends, few colleagues, and of course my own way of looking at this behavior or hunting behavior. So if you think about it, it's hard. Of course, wolves hunt in a 3D world. They can go up and down, left and right, forward or backward. It's a very complicated environment with obstacles, speed, a lot of environmental condition. Let's simplify it to one dimension. Let's say everything is one dimensional. How does the world look like to a gray wolf if it was one dimensional? There is a line here, that's one dimensional. We can't go up and down, no, just left and right. So the prey is here, and if I draw a line, you can see the location of all gray wolves on the left-hand side of the prey. Then in the next step, which is in the photo, I just wanted to show you the photo from one-dimensional perspective. I had this drawing somewhere, I don't know, I've lost it, I think. But I was trying to draw this, say, okay, if the gray is on the right-hand side of the prey, how to update it, whether right-hand side or left-hand side? How do I come up with an equation to move from this side to the other side? Or if it's on the left-hand side to the right-hand side, or in the middle even. You don't have to always go, or from the other side, step away from it. These are the idea that came into my mind, and I played around with a lot of equations and created these 4 equations, and it worked really well. And this one in part B, as you can see, all wolves are around the prey, for this side and for the other side. So they completely encircle the prey. Here we have 5 was 6 on the left-hand side, 1 on the right-hand side. Here we have 3 and 3 again. And at the end, we have 2 on the left-hand side and 3 on the right-hand side. And at the end, when they attack it, I don't have any more photo of that, but imagine when they're attacking and eating on the prey, they are on the prey. That means they converge and fund after going encircling and chasing, harassing. Now they are on the prey. So the location of the gray wolf is the same as the location of the prey. So, and that's what I did. So D is the distance. So imagine the distance between these two. And then the factors allow me to update the position inside that space, on the right-hand side, or even on the left-hand side. So each of these mechanisms will help me to do that. So these equations create this behavior, and we will learn more about it in other videos. So the use of vectors allow me to apply to any dimension, because I was thinking, all right, people are going to apply this algorithm to any sort of optimization problem, right? Maybe they have 20 parameters, 50 parameters. How am I going to handle that many variables? Or can I make it general enough to do that? Then I say, yes, why not? We can make a vector. I'm not going to use dot product, cross product, and things like that. Just two vectors. You can treat each vector independent. Imagine in that last example, I was looking at this dimension. Then if I rotate everything 90 degrees, then I'm working on the y dimension. And when I combine it, then I make a 2D space, just like here, as you can see. So I'm looking at it as a separate dimension, because remember those sliders in the example? That's why I said that example is very helpful, because I link everything to that problem, or that analogy and example. Every slider was one dimension. I was changing it and see, okay, it's very promising, so let's keep it here. But there was one ground truth. That let's say if this is the slider, right? This is slider, and I know this is the ground truth. This is the best solution that I have the best value that I have to find for that the slider. I was dragging the slider left and right, going this side, going that side, until I found that sweet spot around here. And that's exactly what these equations do for me. Look at it from one dimension. Whenever you want to work with these algorithms, or even design a new one, hopefully, treat it as one-dimensional. And then you can build and you can extend it to higher and higher dimensions. 3D dimensions, well, it's the same thing. You've got one slider, two sliders, three sliders. It's the same thing. Or you can apply this equation. You can use this equation multiple times for any sort of dimensions or any sort of variables that you have. Okay? So hunting, the gray wolf have the ability to recognize the location of prey and encircle them. So far, I show you how we can update the position of one gray wolf using those equations. But in reality, we have to also use multiple wolves. Remember, I have alpha, beta, and delta, and those are the three best solutions that we found so far. Now, I'm going to use those three to be able to estimate the location of a prey and update the position of any other gray wolf based on that estimated position. Because it's safe to assume, I should say, that when you have three best solutions for a problem, those are very close to the best solution, or those are the most promising ones. So you don't want to waste your computational resources on other bad solutions. You have to rely on those good solutions. And that's what a lot of stochastic optimization algorithms do. They rely on good solutions, because that's the only way that you can judge whether you are doing something better or not. Anyway, the hunt is usually guided by alpha. The beta and delta might also participate in hunting occasionally. However, in an abstract search space, we have no idea about the location of the prey or the optimum. In order to mathematically simulate the hunting behavior of gray wolf, I suppose that the alpha or best candidate solution, beta and delta have better knowledge about the potential location of the prey. Therefore, we save the first three best solution obtained so far and oblige the other search engine, which are the omegas in this case, to update the position according to the position of the best search engine, or basically the estimated position of the prey. The following equations are proposed in this regard. So I use the same equation as you can see here. See, I've got the same equation, but then I calculated 3 times for alpha, beta, and delta. There we go. I've got the distance to alpha, the distance to beta, the distance to delta with some factors like C and things like that. Then I get the first position for the position that I'm supposed to be if I only follow the alpha, the position that I'm supposed to be if I only follow the beta, and the position that I'm supposed to be if I only follow delta. And how do we consider all of them? I just average them. So x1 plus x2 plus x3 divided by 3. Again, going back to one dimension, okay, think about it. If I have 3 wolves and I want to update the position, I calculate the distance between them and use that equation to find and consider 3 of them, calculate the average, and find a solution somewhere around them, somewhere in the middle of them. Again, these are a bit difficult to explain that way. That's why I have some videos to show you live demos and, literally move some sliders and change these parameters to see how things change, how this algorithm behave. And it's kind of similar to that. So again, in a search space, we don't have the prey, but think about it, these guys are very close to the prey. So if this guy wants to update his position, he or she can rely on them. So it will basically move towards this area. It's an average X-wise. See, I've got this one, 3 numbers, almost correct. Y-wise also a good place. It depends on, of course, the way that you use the equation. But what I'm saying is that we considered the 3 of them and also the equations to update the position. So attacking a prey. Now, we keep updating the position, but at some point we need to also stay away from things. What if those 3 solutions are bad? What if the 3 gray wolves get stuck in one place and a locally optimal solution? There's a way to get rid of it. Gray wolves fringe the hunt by attacking the prey when it stops moving. In order to mathematically model approaching the prey, we decrease the value of A. You need that parameter. Changing A also changes the parameter A, or uppercase A, capital A, and then the value of capital A changes from -2A to 2A. You can set the parameter A yourself, but my experience shows that the best way is to decrease it linearly from 2 to 0. And this diagram shows how this algorithm behaves. When A is between -1 and 1, the position of the gray wolf is inside this distance between the wolf and the prey. And that's some sort of convergence. You're converging toward the prey. But that's not always ideal. In a stochastic algorithm, sometimes you want to diverge because you want to explore better areas, maybe better than where you are, because this might be a locally optimal solution. And that's where the other numbers come into play. So if A is greater than 1 or less than -1, that is where the gray wolf moves outward, moves away from the prey. Or when I'm saying prey here, don't get me wrong, that means the location that is indicated by the 3 best wolves, alpha, beta, and delta. But to make it simple and more intuitive here, I use the term prey, and I use an icon of a buffalo. So, and I think that is everything. Just quickly, how the gray wolves in the gray wolf optimizer search for prey. Gray wolves mostly search according to the position of alpha, beta, and delta, as I said. They diverge from each other to search for the prey and converge to attack the prey, that they constantly do that. And the magnitude of this reduces over time to focus more on convergence rather than divergence. For divergence, we utilize A with random values greater than 1 or less than -1 to apply search result to diverge from the prey. This emphasizes the exploration that allows the GWO to search globally. So there are 2 terms here that I have to focus on: exploration and exploitation. In exploration, you can find these terms in machine learning and other sub-areas of AI too. In exploration, you try to explore things. That means if this is the rectangular that you want to find a solution inside it, you try to stochastically and randomly discover as many places as you can. So the search is broad. Whereas in exploitation, you focus on one area and your search is more local, or your optimization is more local rather than the global. So another component of GW that favor exploration is C. C is a vector contains random values between 0 and 2. So remember, A and uppercase A changes from 2 to 0, lowercase from 2 to 0, and uppercase A random number between -2A to 2A, but the impact or the magnitude of changes reduces slowly over time. So that means chances are that at the end of the iteration, you got stuck at point, but that point is not the best point. So I needed some sort of mechanism, another mechanism to make it a little bit more stochastic, because there might be something that changes constantly randomly without the impact, without changing it based on the iteration. Doesn't matter if you are in the first iteration or last iteration, chances are that you are trapped in locally optimal solutions. So there must be a mechanism to combat those kind of situations. And I came up with the parameter C. Parameter C is calculated by a component, a random component called R1, or R2 in this case, my bad. This is the equation. Remember, C is equal to 2 times R2. So it's a random number between 0 to 2. And based on the number, this component provides random weight for the prey in order to stochastically emphasize or de-emphasize the effect of prey in defining the distance. So if the C is greater than 0, there's an emphasize on the impact of the prey, the position of prey on the position updating. So I mean, things get attracted to the prey. But if it's less than that, then not really. And switching between that, minus less than 1, greater than 1, less than or greater than 1 is done stochastically, and it doesn't change based on the iteration. So it provides always that sort of mechanism. This assists GWO to show a more random behavior throughout optimization, favoring exploration and local optimal avoidance. C is not linear decrease in contrast to A. In contrast to A, we deliberately require C to provide random values at all times in order to emphasize exploration, not only during the initial iteration, but also final iteration. This component is very helpful in case of local optimal stagnation, especially in the final iteration. And that's pretty much for this video. I wanted to just go through these ideas and these equations. Always look at things from one dimension and things make sense. A lot more makes sense, and then you can build based on that. So here's the pseudocode of the gray wolf optimizer. We're going to be coding it later on, but just quickly as a pseudocode, you initialize a population of wolves. Gray wolf optimizer is a population-based algorithm, which means we have multiple solutions in each iteration. We initialize A, uppercase A and C. Again, uppercase A is calculated based on A, so technically you just need to create A and initialize A, and things get calculated based on that. And you also need to randomize 2 parameters, R1 and R2. I didn't have it here because those are some internal variables, internal mechanisms. The source code would have been very lengthy if I include everything. Anyway, we calculate the fitness of each search agent, which means we use the objective function or cost function to calculate the fitness value, objective value, or cost value for each solution. So if you have 10 gray wolf, you should have 10 also optimal. Sorry, not optimal values, objective value for each. Then we choose the best 3. We assume the best solution is alpha, second best solution is beta, and third best solution is delta. And over the course of iteration, while a stopping condition is not met, which is in this case to hit the maximum number of iteration, for each agent, we update the position of the current agent based on those 3 equations. We update those parameters. We calculate the fitness again. We update XA, XB, and X alpha, and we go to the next iteration. So we keep updating alpha, beta, delta if we find a better solution, and also keep updating the solution around it. In one dimension, it will be just left and right. And by the time that you finish the while loop, you return the alpha as the best optimal solution that you can estimate for this problem. Why am I saying estimate? To estimate, that's because it's a stochastic algorithm. You're trying to estimate the global optimum for an optimization problem, or you're trying to find a minimum in the case of our example for the cost function. You don't know where it is, but with these mechanisms, you can get very close to the final solution. And that's pretty much everything for this video. Let's stop here and move on to other videos. The next few videos are very interesting. I've written a lot of codes in P5 to show you how these equations work. And you will understand, and I can guarantee that you will master the equations of the gray wolf optimizer after watching those videos. Thanks a lot.